Now we're going to look at an example from beginning to end without all the explanatory material in between. This example is called the example. It's a hypothetical situation in which we have students who are going to try to predict their final exam score given certain information. Alright, so the y variable is the final exam score. Alright, y is always the variable to be predicted or explained. It's a number between 0 and 100. We're going to use two x variables to help us with that explanation. First is the homework score. Again, it's a number between, say, 0 and 100. And x2, the midterm score. Similarly, some number between 0 and 100. So in this hypothetical situation, we're sitting there, say, before the final exam, and we have two bits of information, homework score and the midterm, and we want to plug those into a formula and predict the final exam score. Of course, to do that, we need a set of data in which we have all the data, final exam score, homework, and midterm. Run the estimated regression, find the estimated regression, and so that we can have a machine or an engine for prediction. Alright, let's have a look at the mini-tab output. Okay, at the beginning it tells you about your variables. There are 29 observations. At the end of this file it tells us about the estimated regression. Okay. Alright, from this situation we can find the values for the beta hat 0, the 5.8, beta hat 1.508, and the beta hat 2.377. We could find it there or in the routine type of table that regression outputs have, where you have, in this case, the coefficient column 5.8, 0.5082, 0.3767 for the beta hat 0, beta hat 1, beta hat 2. Beside those we have the standard errors. Alright, and from that we'll also take the R squared and the fact that we have 29 observations. So let's go back to our sheet and write that information down. Y hat is equal to 5.8 for the intercept plus 0.508 x1 plus 0.377 x2, and we'll write the standard errors below the coefficients in parentheses as is normal. Standard error for beta hat 1.2602 and standard error for beta hat 2 is 0.1402. The other information that we'll take from the output is that the R squared 41.5%, which is not very good, yet the regression may be significant, and we'll take that the N is 25. Alright, so we're going to do technical analysis in the proper order. Let's just give it the title here, regression multiple regression, the basic technical analysis. Alright, what are we going to do, of course, in the basic technical analysis? First, look at the R squared and its interpretation. In this example, we are given the R squared, and so there's nothing to calculate. But in an example where the R squared is not given, we would calculate it from the other given information and then do the interpretation. So in this case, just the interpretation is necessary. Alright, 41.5%. So the interpretation goes something like this. This regression, that means the equation that we have above, the y hat equals 5.8 plus 0.508 x1 plus 0.377 x2, that exact regression equation explains the 41.5% of the variance in the y variable. Instead of saying y variable, we'll write down what it is in the final exam score. Okay, and that's it. Don't have to embellish it by telling anybody what the x variables are. The x variables are contained in the expression, this regression. Okay? Alright, so that's the interpretation of the r squared. And as before, that r squared is not very good. Second, we'll do the F test for the significance of the regression. There's the whole equation. Alright, and this goes the same way every time. Null hypothesis will be that all the beta i's in the regression are equal to 0. That means that no x sub I in the regression explains the y. Alternatively, at least one of the betas is not 0, which means at least one x explains the y. Next thing we have to worry about is degrees of freedom on the F. F has 2 degrees of freedom, n for the top line and n minus k minus 1 for the bottom line. K, as always, is the number of x variables in the regression. We have clearly 2 x variables in the regression, so first degree of freedom there is 2, and then n minus k minus 1, n is 29 minus 2 minus 1, and that works out to 2 and 26 degrees of freedom. Okay, we do a basic simple test. Let's draw a representation of the F distribution. Alright, so we're going to go to the F tables, look up the critical F value on our tables, which have an alpha of 5%, so that's 2 and 26. Alright, so let's go to our tables and look that value up. Alright, so this is the F distribution with an alpha of 5%. That's the only thing we have on our website. So the second column is where the 2 degrees of freedom for the top line, and then we want 26 for the bottom line. So our critical value is 3.37. Okay, so critical value 3.37. Any F-calc below that and the regression is insignificant. Anything above that and the regression is significant. Okay, and let's write that down. A quick decision rule: if F-calc from the regression is less than or equal to the critical value 3.37. Okay, we'll say simply that the regression is insignificant, meaning that there could be no explanatory power there, or the explanatory power is so weak that we can't tell if there is anything there or not. Alternatively, if f-calc is greater than the critical value 3.37, then the regression is significant. The more significant, the better the predictions will be. Next step is to do f-calc. In this case, since we're given only r squared, we're forced to use the r squared version of the formula. So that'll be r squared divided by k, all that divided by 1 minus r squared divided by n minus k minus 1. Alright, above we had r squared was 41.5%. When we entered in this formula, though, we changed it back to a proportion, 0.415, and since the concept was already squared, we don't square it again. Divided by the 2 degrees of freedom up there, divided by 1 minus r squared being 0.415, divided by the degrees of freedom in the bottom row, 26, and that works out to be 9.222. 9.222 is clearly greater than the critical value of 3.37, so we'll say quickly for the decision that the regression is significant. Okay, now we've finished with our f-test.